I'm not going to concentrate on graphing today, but I think with this example, only because it's such a basic rational function with which you're so darn familiar. Clearly, it's a rational function in which the numerator is of degree less than the denominator as polynomials. So I get a horizontal asymptote for 3 on the x-axis. I think there's a vertical asymptote clearly at x equals -1. And if I were to build a sine graph for the y values, here's a number line, and I'll plot the zeros of both my denominator and my numerator. Those two real numbers subdivide the real number line into 2 subintervals. Well, 3 subintervals, excuse me. I'll check them. If x is a billion, clearly everything's positive. Now, not checking the remaining intervals. That is a zero of a linear factor, upstairs or downstairs, raised to an odd power, so it will act as a toggle switch. This is zero of a linear factor, upstairs and downstairs, raised to an even power, so it will not act as a toggle switch. What the sine graph really tells me is that the graph of this function is below the x-axis over these 2 intervals, above the x-axis here. So it must look something like this. The x-intercept's located at 2, 0, so does that mean it looks like this? So my x-intercept's located here. Don't worry if my scaling's off, I don't care about that. Now, what I want to do is talk about an interesting point right here, where certainly it has to be the case that I have a local max. For me to find a local max, I will compute the first derivative function and build a sine graph for it. So differentiate with my quotient rule. Simplify. Continuing to simplify. Now take a peek at how I've generated 2 critical numbers. Building a number line, apply those zeros, and checking my intervals. That may be the sine graph of the first derivative function, but what it says about the original function is that I changed from decreasing to increasing to decreasing about those critical numbers. Now keep in mind, at x equals -1, that's not really in a domain of my function, so it does not yield a local min. But 5 is in the domain, so it yields a local max. So now I can identify exactly where this local max occurs. It occurs at the point whose x coordinate is 5, whose y coordinate can be found by plugging 5 in for x here. Is that 3 over 36? I think 1 over 12. Now for me to discuss concavity, looks to me like I'll be concave down, and then change somewhere over here to be concave up about some inflection point. But I'm running out of room. So allow me to bring this up top. And I will build a sine graph for the second derivative function. I will plot the 2 zeros I have upstairs and downstairs and build a sine graph. What this means is that my curve is concave down over this interval, but concave up over that interval. So it looks to me like my inflection point, by the way, that should be 8 out of 4. Looks to me like I have an inflection point at 8 comma something, and the something is 6 divided by 36. That reduces down to 1/6. Actually, 781. Regardless of what it is, but you can simplify.